Okay, this video is going to talk about special right triangles. The first one I'm going to talk about is a 45, 45, 90 triangle. This can be obtained by taking a square and cutting it in half. So let me start with a square, the best square I can draw. And one of the things that we know about a square is that it has four 90-degree angles. So I'm going to draw this in here. Another thing that we know about a square is that all of the sides have the same length. Now if I took this square and I went from one corner to the opposite corner and cut it in half, if you look at the angles now, I still have the 90 degree down here, but the other two 90 degrees were cut in half. This one's 45, this one's 45. But I have the two legs now of this right triangle are the exact same length. So let me erase this other side of the square. And we could talk about the 45, 45, 90 triangle. I have two legs. The two legs of a 45, 45, 90 triangle are always the same length. So let's find out what the hypotenuse is, this part right here. We're going to use the Pythagorean theorem. Pythagorean theorem says if you take the two legs, a squared plus b squared, it should be equal to the hypotenuse squared. Well, we know that both of the legs are the same length, so I can replace that b squared with another a squared. A squared and a squared are like terms that can be combined. I'll add them. I have 2a squared is equal to c squared. Now if I want to find out what c is, I'll take the square root of both sides. I'm going to switch sides here too. C is now equal to the square root of 2a squared. If I want to simplify this, I could pull the a out and c would be equal to a square root of 2. So this side over here, rather than writing it as c, I'm going to write it as a square root of 2. Now what we've done is we use the Pythagorean theorem and we use the ratio of the sides of a 45, 45, 90 triangle to write the side lengths using one variable. Rather than a, b, and c, we're using only a. So let's try using this in a problem. I've got a long problem next. Right here. Okay, the mat used for floor exercises at a gymnastics competition is a square with side lengths of 12 meters. A gymnast starts at one corner of the mat and does a tumbling routine across or along the diagonal to the opposite corner. To the nearest meter, how long is the gymnast's path? All right, well, that's easy enough because what we're talking about here is the right triangle, 45, 45, 90. Here's my 90. This is the path of the gymnast. You can actually see in the picture the line where they go back and forth from corner to corner. It's kind of funny. And that's the path they take. Now, this side here is 12 meters. If that is, so is this one over here, because the two have to be the same. So, the hypotenuse is the leg times the square root of 2. Or, we wrote it as a square root of 2. So that would just be 12 square root of 2, which in your calculator will give you to the nearest meter, because it did say in here to the nearest meter, 17 meters. Makes figuring out a problem like this very, very easy. All right, let's go on to the next triangle. The next one is a 30, 60, 90 triangle. For a 30, 60, 90, this one could be obtained by cutting an equilateral triangle in half. So let me try and draw an equilateral triangle the best I can. That's not too bad. All right, one of the things that we know about an equilateral triangle is that all of the angles are the same. They all add up to 60 degrees because the sum of them have to be 180 degrees. We also know that all of the sides have the exact same length. This time, instead of calling them A, I'm going to say they are 2A. It doesn't really matter what I call it. I can call it X, I can call it whatever. Hopefully this will be clear why I'm doing this in just a minute. So this is 2A. Now, if I take the vertex of one of the angles and I draw a line perpendicular to the opposite side, like so, I'm creating a 90-degree angle down here. And the 60-degree angle up at the top has now been split into two 30-degree angles. Let me erase that 60 if I can. There. Has now been split into two 30-degree angles. And I have a 30, 60, 90 triangle. Now hopefully you'll see why I use 2A instead of just A. Because now that means that this side is A and this side is A. When you add them together, you have the 2A. Alright. Knowing that, we could find out this other leg over here, which typically would be B using Pythagorean theorem. So I have A squared plus B squared is equal to C squared. C, though, is the hypotenuse, and I already said that that's 2A. So now what I have is A squared plus B squared is equal to 2A squared. 2A squared, when you do that, you square the integer and the variable. So 2 squared is 4. A squared is A squared. A squared plus B squared. Now I want to subtract. I'm trying to solve for B, so I'm going to subtract A squared from both sides. That leaves B squared on the left. 4A squared minus another A squared gives me 3A squared. Then I'll take the root of both sides. B is equal to square root of 3A squared. I can take the A out of there, and B is now A square root of 3. So I can replace this B in the middle. In fact, I'm going to erase this whole side of this equilateral triangle. And over on this side, instead of B, I have A square root of 3. So again, instead of using A, B, and C, now I'm using just the variable A, which is kind of nice. Let's use this one in a problem. Let's look at MIT's Building 66. It's approximately a 30, 60, 90 triangle. The length of the hypotenuse of the triangle is about 294 feet. Find to the greatest, or to the nearest foot, the lengths of the legs of the triangle. Now see, here's the thing. The Pythagorean theorem, we had A, B, and C. If we were missing one, we could find the other one. It wouldn't work that good if we're missing two. But here, we are given a length of only one, and we need to find the other two. Because we wrote these, because we solved these with using one variable, if we have one of the sides, we could find the other two. So I'm going to try and draw in here. This is right on this side here. So let's say this is the 294 right here. I don't know that it is for sure. Let's say it is. In fact, let me try and draw an aerial view of this 30, 60, 90. Okay, and I'm going to assume that this here is the 294. And we know that this over here is A, and we know that this over here is our other leg, our B, or actually we wrote it as A square root of 3. Now remember that the hypotenuse over here is 2A. So if we took 294, what we could do is we could say, now let's take 294 and divide it in half. A then over here is 147. If A is 147, then this side is 147 square root of 3. So in other words, this side is exactly, well, it's about 147 feet. But this one, 147 square root of 3, is going to be, to the nearest foot, 255 feet. It's a very nice way to do this. Again, if you're not quite getting how this is useful to have just the one variable, let's take a look at the next couple problems. Here, whoa, don't look at a puzzler. You didn't see that. You didn't see that. Okay. Find the unknown lengths. Write your answer in simplest form. So I have 30, 60, 90, another 30, 60, 90, and then a 45, 45, 90. So what I'm going to do is I'm going to say, all right, well, what if I said, I just gave you this, and you wanted to find the other two? Again, it's with only one variable, so it makes it very easy to do. And you can't do that with the Pythagorean theorem. So what we'll do, this is 2a, so up here this is just 18, and this is going to be 9 square root of 3. And there you go. Now you have the other sides. Now let's assume that, and it's in simplest form as well, let's assume that this is a right angle. Up here this is a 30 degree, this is a 60 degree, here's my 45, here's my 90, there's my 45. Okay. What I want you to do is I'm going to give you, which one should I give you? Okay, I'll give you this. I'll give you this down here, 6. And what I want you to do is I want you to find the other 2, and then I'll give you on this one, 7. And I want you to find the other 2. Doesn't matter what the units are. If you want to pause the video real quick and try and do those, using just the information that we learned today with the single variable. Pause the video and then play it when you're ready. Okay, here my base is a, so this side, this other leg over here is a square root of 3, so I have 6 square root of 3. And then the hypotenuse is 2a, so this is going to be 12. For the 45, 45, 90 triangle, the 2 legs are exactly the same, so this one's 7. And then the hypotenuse is going to be a square root of 2, or 7 square root of 2. The key thing to remember here, and I'll write it down because I don't think you guys are writing everything I say. In both of the 2 types of special right triangles, the ratios of the side lengths are always the same. That's the key concept. That's what you want to understand. So when you see these, you can always apply this. All right, now it's time for the Daily Puzzler. Puzzler. What do you know about the lengths of the sides of an equilateral right triangle? That is all. Have a great day, everybody.